So we have the pleasure to start this PGMO lecture. So PGMO is a corporate sponsorship program operated by Fondation Mathématiques NMR with the support of Electricité de France. So we thank our sponsor, Electricité de France, and we also thank École Polytechnique en Andrea for the organization of the lecture. So now we have the pleasure to introduce François DELARUE, professor at Université de Nice, who will make this exceptional lecture on mean-field games.
So thank you, Stefan. Thank you to the organizers. So there will be 4 lectures on mean-field games. And so the first one this morning will be about the formulation of mean-field games, and then the analysis studying the solvability of those mean-field games. And then in the afternoon, we will have a look at other formulations of mean-field games. So the very basic purpose, as you see on the slide, is to describe large interacting particle systems, but you have some features in these systems. And as you see, the first one is that, and let me use the pointer. This will be better for people who are online, if I can find it. So the very key point is that the particles are controlled. So you have many particles, but those particles are players in the sense that each of them is willing to minimize a given cost, and so they are controlled. And plus you have the fact that for sure those particles are in interaction, and the mean-field interaction is to say that the type of interaction that you have between the particles is symmetric. And you will see that the symmetry assumption will play a key role in the analysis. And this is exactly what we call by mean-field. And so once again, every player is given a cost functional, and then you want to find equilibria within the population. And once again, equilibria when the population is very large. And so what you are going to say first is that you assume that somehow the population is infinite. And so what can you say when the population is infinite? What is the shape of an equilibrium? And then how to come back to the original model when the number of players is very large, but is finite. So this is the very general philosophy for this kind of problem. But as you will see, the very first thing that you have to do is to define the notion of equilibrium. What does it mean precisely? That you have an equilibrium within a population of particles, each of them trying to minimize in a given sense that I should specify, I should clarify the sense of the word equilibrium. And in fact, the very basic philosophy is to say that we may have in practice 2 kinds of equilibria. The very first one is a notion from game theory, which is a notion of Nash equilibrium, which means that within the population, you want to find compromises. Somehow players are competing and they're individual or individualistic, and each of them is willing to minimize a wrong cost, and regardless the cost of the others, in the sense that they don't care if the cost of the others is higher. So this is a selfish point of view. And there is another point of view, which is to say, no, now you assume that the players obey a given chief or a central planner. This is what I call here a common center of decision. And so all the players try to cooperate to minimize the cost to the society or the cost to the collectivity. And you realize that you don't have exactly the same problems for sure at the level of optimization. And you will see that mean-field game corresponds to the case when, once again, you want to find compromises between competing individuals. But I will show you another formulation of another problem, which is what people call mean-field control, which is a bit different. And I will show you that there are connections between the 2 of them. They are connected not only from the modeling point of view, but also from the mathematical point of view. And so once again, the key question is to say what happens asymptotically when the number of players tend to infinity. So these are 4 typical pictures that you can have as practical applications. So the very first one on the top this is the whole of, I guess, of an airport or maybe a train station. And you assume that there is a very bad event that occurs at some time, so a kind of fire, for instance, that occurs in the hall, and then everybody wants to leave as fast as possible. You want to leave the hall, and so what you control is your velocity. So you want to reach as fast as possible the exit doors that are in the hall or in the room. But for sure, you see the others because there might be some effect of congestion in the population. And so when you see the others, you see that in a kind of symmetric way because you don't really care about who is where, but you care about the shape of the density in the population, and you see the whole collectively, or the rest collectively. And what you want to minimize for sure is the exit time, so the time that you take to leave the hall. So this is one first instance of a mean field game. Then you find for a consensus, and you see that in this model, things are dynamical. So this is another feature of the model that we are going to study. These are dynamical games or dynamical control problems. Another example, which is very related. Sorry, let me use the pointer. So this is a very famous example in the original lectures. I'm going to give a few names for the bibliography, but let me say that this theory comes back to the works of Lasry and Lyons, and this is one of the favorite examples in the lectures of Lyons at the Collège de France. So for those of you who know this, this is La Place de l'Étoile. And so once again, what you want to do is to cross as fast as possible the roundabout. And so once again, you find a compromise and you see the others through the collective state of the population. You don't care exactly about who is where, but you care about the global state of the population. Here you have on the pane at the bottom and the left, here this is another kind of mean field game, but maybe a little bit more complicated in relation with the energy markets. So in fact, you have people living in a building, but you see that on the top of the building, you have solar panels. And so you can guess of these people as being consumers of electricity, but at the same time, they are producers of electricity. And when they consume electricity, maybe they consume the electricity that they produce, but maybe they also consume the electricity that is produced by a global producer. And so the interaction between the global producer and these small producers will occur through the price of electricity. And so you have an interaction through an aggregate quantity that describes in some way, the state of the collectivity. And this is again a kind of mean field interaction. People see each other through an aggregate quantity, which is the price. And so you are looking for a compromise. Here, this is maybe this is a different kind of pictures. This is to say that recently you have more and more works at the intersection between mean field control and machine learning. This is a way to try to understand the behavior of some neural networks by using the tools of mean field control. The idea behind is to say that when you have many neurons in a neural network, then you can try to describe the global state of all the neurons, so the statistical state of the neurons, instead of the state of each neuron individually. And so there were some very famous papers that appeared 3 or 4 years ago by Montanari, for instance, on these approaches. So you have 4 possible pictures in the literature. So now let me give you a few words about the program. So once again, the idea is to come back to a large population and to try to let the number of players or particles, if you prefer, tend to infinity in this population. And the reason why you do that is that you expect to benefit from the symmetry of the interaction to obtain some averaging phenomenon. And these averaging phenomenon, from a statistical point of view, they should be connected with a law of large numbers. So if you have a law of large numbers, certainly the question is that you may have in mind is, where does the randomness come from in my models? They may come from the original states of the population. Assume that you have around about, it depends on where are the cars at the entry of the roundabout, or also the statistical features of the model may come from possible shocks that you have in the model. And you will see that we will have two kinds of noises in our models, some individual noises and some common noises. And those common noises are going to impact the whole population, and the individual noises are going to impact only individually the particles. And once again, by combining symmetry and averaging, you expect to be able to pass to the limits, and certainly this should simplify the analysis. This should simplify the model. It seems to be complicated to understand why this should simplify the model, but precisely because when you take the law of large numbers, this is a way to replace some interactions just by means, by average quantities, and possibly this is a way to decrease the complexity of the models. And this is something that is very interesting from the computational point of view, because as you will see, solving a game with many, many players is something that is very difficult from a numerical point of view. So the very first reason why you should go to the number of players tends to infinity is that this should be a way to decrease the complexity of the model. Okay. So this is the program. First, I'm going to try to explain to you what should be an asymptotic formulation for this kind of mean-field games. And then we will wonder about existence of equilibria, uniqueness of equilibria, and also about the shape of these equilibria, and possibly how to come back to finite models. For those of you who know a bit of particle systems, when you try to pass to the limit on the number of particles, and you formulate a possible asymptotic problem for your original model, at the end of the day, you want to see how far the limiting model is from the original one. And this will be a question that we will study tomorrow. A few names of people who have been working in the field. So I have to say that it comes back to two groups of people. The most famous ones in France certainly are Lastry and Nyon. So the first papers released by these two people appeared in 2006, so more than 15 years ago. And then you had a series of lectures by Lyons at the Collège de France, and you still have those lectures which are available on the website of the Collège de France, and certainly this is very good to have a look at them. So I guess you have maybe around 4 years of lectures. About these lectures, let me just mention that Cardaliaguet, who is a very famous name in the field, together with Alessio Porretta, they just released in a booklet by Springer a very, very nice survey of mean-field models. This is around 100 pages. And at the end of this survey, you will see that they do a kind of bibliography of the lectures by Lyon. So you can find what are the topics in the lectures by Lyon in his lectures at the Collège de France. And so you can find this in the nice survey written by Cardaliaguet. And once again, this appeared in 21 in a Springer booklet. So this one is a very good entry to the theory. Another group of people who studied originally mean-field games, these are those Canadian people, Ron Keynes and Malame. So you have them here. And maybe there are more from the engineering point of view. So you have more models connected to engineering, and this might be interesting to see, or to come back to their original point of view to see some practical motivations. And then you have possibly two groups of people depending on their feelings, on their tastes. So you have PD people, so you recognize, and some of them are here, like Charles Bertucci. So I mentioned Pierre Cardaliaguet. Yves Ajdou did a lot on the numerical point of view. Gangbo did as well, Gomez, Alessio Porretta. And on the probabilistic side, so I did some papers with my colleague René Carmona. Alekos Cekin, who was a postdoc at the CEMAP, did a lot as well. Fabrice Jete, who is now in CEMAP, is also working on these equations. And I have to say that one very productive researcher was or is Daniel Laker in New York, and he was a former student of René Carmona. But since his PhD, he has been doing a lot in the theory, and so certainly he did some surveys as well on his own works, and I really encourage you to have a look at what he did if you want to enter the theory. This is absolutely nice. So this is for mean-field games. And about the other kind of optimization, which I'm going to mention, but certainly I will spend less time. This is what people call optimal control of Makin-Vlasov equation. So this is nice for you if you know what a Makin-Vlasov equation is. Sorry about this. And another terminology is mean field control. This is just below this thing that I'm not able to remove. So mean field control. So you have mean field just before control. So maybe now this is a more famous word for optimal control of Makin-Vlasov equation, but let's say that this is the same. And this is another theory that is very productive at this time. In France, I have to mention Yuan Pham. He did a lot, or he has been doing a lot. And at the CEMAP, Nizar for sure is working as well on these types of problems. Okay, so this has been a field that has been growing very, very fast, and now you have many directions in analysis, probability, PDEs, optimal transportation, calculus of variations, and certainly this is one of the reasons why the field has been growing so fast. This is at the intersection between many things. Let me come back to the original motivation and try to give you some equations for what we want to be. So now let's go to maths. So let me come back to a particle system. So I told you before that we had in mind to study a controlled particle system. And so the question is, what could be dynamics for this? So this will be very simple models. And once you have understood the strategy or the philosophy, you can adapt and you can generalize the models. I will tell you at some point how you could generalize, but let's say that this is another way or another reason why you have new works coming every year in the field, because you can generalize the models that I'm going to introduce today. So think of the following particle system. So you see that in the particle system that you have here, you have capital N particles. So here N is fixed. So you have a finite number of particles. So I have not addressed first the limit. And so capital X here, this is the state of one player I. You see the index or the label I at time t. And so you see that xi, which is in dimension d, so this is just in the of finite dimension, this is evolving according to some equation. And very simply, I'm going to postulate an ordinary or a stochastic equation. If this is stochastic, it means that there are some shocks in the dynamics. So I'm going to do that in the rest of the talks. You will see a dynamics given by a stochastic differential equation. You could generalize having some jumps or different things. So I'm going to restrict myself to this framework, but once again, you could generalize. And so you recognize in the dynamics 3 terms. The top one, this is something that everybody knows. This is a drift. The drift is denoted by B. And so in the drift, you see that there are 3 inputs. The first one, very classic. This is the state of the particle at the same time t. So this is just the velocity of the individual. And as I told you before, this velocity field is controlled. And the notation for the control in my lectures will be alpha I t. So alpha I, this is the choice of the control at time t by player I. Everybody is choosing a home control, and so depending on who you are, you have another choice of the control. And in red, in B, you have this red term. You see at the same time the global state of the population. So you have your velocity field. It depends on your state, on the choice of your control, but also on the states of the others. And now the key point in the rest of the lecture, which is to formalize what I mean by the rest of the population. And I have to say how I see the other players in the population. And so this will be the point where mean field is coming in the rest of my talk. Now you have two other lines. So you have these two terms. The first one is dwi, which is the derivative of a small increment of a Brownian motion. And you see that there is a label I. This is to say that this is an individual noise that only impacts the dynamics of player I. In statistics, you could say that these are idiosyncratic noises. I'm going to say that these are individual noises. This is slightly easier to say. And the key feature is that those noises are independent. So everybody has its or her own shocks. And you may have a volatility or a diffusion. It might depend on the state of the player itself, on the global state of the population. You could also assume that it depends on the control itself. But if you know a bit of stochastic control, you know that when the volatility depends on the control, things are a little bit more difficult to study. Anyway, you have more and more papers allowing for sigma, so for this volatility coefficient, to depend on alpha. But this is something that I'm not going to do. But if you are interested in this direction, you may find recent papers in this direction. And the last line, this is very similar, but now you see that the noise that you have is the same for all the particles. And this is what people call in the field a common noise. So all the particles are feeling the same noise. So now this is a noise that is acting on a macroscopic level because the whole population is going to be randomized under the impact of this common noise. So you see that the distinction between Wi on the one side and B on the other side, this is a way to say that you may have correlation between the noises. So this is a way to simplify the shape of those correlations. And for the volatility, you have the same structure and you could complexify. The impact of the common noise is something that is very, very interesting, and you have more and more works in this direction in the literature, and I will tell you more tomorrow about this in the final lecture, about the benefit that you can have in the you can have from this additional common noise. Okay, so just to say here, just a little bit of mathematical setting. The noises, to simplify, they take values in the same space as X. You could generalize. I'm going to assume them to be Brownian motion, and they are independent. So there is no trap, no big deal, no difficulty here. And you assume that the control are progressively measurable. So you know this, you don't have to anticipate on the future of the noises. This is absolutely standard, and this is not where you have the difficulty in the model. They take values in a given set A. I'm going to take A as being the Euclidean space most of the time. And you can think as a very, very simple model, B of alpha as being alpha itself. So you control the velocity directly. So this will be one model that I'm going to use from time to time next. As for the initial condition, there might be deterministic, there might be random. If they are random, you can complexify, but something that is very, very simple is to assume that the initial conditions are IID. Very simple. Okay, so you have a law of large numbers on this, on the law of these original initial conditions. Precisely, let me introduce an object that is absolutely fundamental in mean field models. If you know mean field models, for sure you know this. And there are some experts of mean field models in the room. If you don't know mean field models, this is the first key object that you have to remember for the rest of these lectures. So this is what we call the empirical measure. You know this from probability or statistics. So what you do is that at any time t, you summarize the global state of the population by means of a probability measure. And somehow what you say is that you put a delta mass at which point where you have one individual in your population, and everybody shares the same mass, 1 over n. So this is a uniform distribution on the players. Just to remember or to refresh your mind, for sure you know this. If these are the initial conditions, so t is equal to 0, these are the empirical measure of the original conditions. If those initial conditions are IID, then when n tends to infinity, this converges towards the theoretical distribution of the population. I'm going to use this next, but for sure this is one object that you know from probability theory. Okay, another key object is that you are going to introduce the space of probability measures, P of RD. Sometimes you will see appearing an index 2. This is just to say that I'm going to focus on probability measures with a finite second moment. So if you think of a random variable that is associated with a probability measure in P2, it means that the square is integrable. This is very convenient from a mathematical point of view, not only for control, but also for the analysis of the space of probability measures. I'm going to speak about this in the afternoon. And this is very convenient to have a square integrability property. This is technical, but useful from a mathematical point of view. Okay. And what I'm going to do, let me just start with the bottom equation on the slide. So back to the previous dynamics you have in the particle system. What I mean by the global state of the population, so the way one individual sees the others in the drift and in the volatility or diffusion coefficient, is that I'm going to assume that the dependence occurs through the empirical states of the population. So you see that in the coefficient I have, so this is precisely mu bar nt that I see. So I see the others through the collective states of the population. And once again, the key fact is that this collective state is summarized by means of the empirical distribution. And so you have this in B, you have this in sigma, and in sigma naught, which is the volatility driving B. One thing that you should realize at this stage is that there is a lot of symmetry between the particles. Everybody is using the same B, the same sigma, and the same sigma naught. So you see that there is a lot of symmetry between the particles, and this is precisely the point that I'm going to use next to pass to the limit. This would be completely different if I had sigma depending on I or B depending on I. The story would be different. But somehow here, the labels are more or less blind. I can focus on player I is equal to 1, or I is equal to 2, or I is equal to 3. Somehow, I use the same B, the same sigma 0. So I'm going to regard things which are quite symmetrical. For sure, the difference between all of them is that they can tune or they can implement different controls. So here you can have some heterogeneity between the agent because they can tune different controls. Okay, so B is a function, and this would be the same for sigma and sigma naught. B is a function of your private state, of the state of the population, and of the choice of your own control at a given time. So now one question that you could have is, well, what does it mean to have a function depending on X, on a measure mu, and on a control alpha? It looks to be a very complicated object. So I'm going to give you two instances of this. And these are typical in min-field models, but if you don't know min-field models, I think that this is very useful. The very first example that you have in the literature is that when you see the orders, so you see that you have B of mu here. In fact, what you see is a function of the action of mu on a given test function. Typically, what you have in finance is you see the variance, for instance. So this is not exactly a phi of mu, but this would be a function of the mean and the second order moment. So this is typically the variance, or the mean state of the population. So phi is the identity. So these are typical examples that you have. So you see the others, or the dependence on the state of the others through the action of a test function phi, which is fixed onto the measure mu. This is one instance. Another instance, this is a kind of convolution. This is not exactly a convolution, but I could write this as a convolution. So you see that I replace here mu by v. So now, in fact, this is a quite bad notation. This is not the same b, but this is to say that you can construct b of mu in this way. So you see that you take b now depending on the second argument in RD. and you integrate this second argument with respect to mu itself. If you take B of X and V as B of X minus V, this is typically what you have in convolution. And this is a way to compute forms of potential energy. So you see the orders and you compute your potential by, let's say, computing some distance or some square distance or whatever, depending on the kind type of energy that you have, or other kind of potentials, I don't know. So the distance between X, your private state, and the rest of the population by means of this kernel B. So this is the kind of functionals that you have for B, sigma, and sigma naught. Now everybody is receiving a cost. So this is something that I have not described so far. So any particle in the population has a cost. So the cost depends on the label of a player. So you see that you have this little I here, and so this I, and you see that in the notation Ji, I'm seeing the cost to the player I. The very first thing is that my cost is going to depend on the choices of all the other particles in the system. So for sure, it depends on my own control, but I also see the controls of the others. Very simple reason is that my dynamics may depend on the others. So when the others have chosen some control, I see the impact on the dynamics. But in fact, even if B doesn't depend on mu, even if sigma and sigma naught do not depend on mu, I would have the same just by assuming that in the cost functional, the coefficients depend on the state of the population. And in fact, this is the very basic model that you have in mean field games that I'm going to describe next. So in the cost functional, the form of the cost functional is typical of what you have in optimal control or in stochastic control theory. You have a terminal cost, okay? And in the terminal cost, you see, once again, this is a function depending on the state of I at time t and the state of the population at the same terminal time. Once again, you may think of a convolution. You compute the mean distance between your state and the state of the others. And you have what we call a running cost. So you make the sum between 0 and t of some infinitesimal cost that you have to pay. And so this terminal cost, running cost, once again, it depends on X, the state of the population, and the choice of your control. So if you know stochastic control, this is a generalization of it. But now the key point is that in the cost, you see the others through the state of the population. So I insist on the fact that even if B and sigma naught do not depend on the state of the population, Ji depends on the choices of the others, so on the other actions, because G and F do depend on the state of the population. Okay, so this is one form of example that you will find in the literature. So as a kind of interaction, you have a kind of potential interaction between Xi and the rest of the population through a convolution kernel. So G is a function on RD and F is a function on RD, and you compute the cost in this way. And you have in the red term, you have a kind of kinetic energy. You compute the square of the control. This is a very basic model. And as for Xi, you could say that B is just alpha and sigma is 1 and sigma naught is 0. This would be a very, very simple model in practice. Okay, now the question is to say, in this particle system, I want to find for an equilibrium. And as I told you before, there could be several ways to define an equilibrium. And the very first notion that I'm going to introduce or to use is the notion of Nash equilibrium. So this is a notion of compromise. Everybody is trying to minimize its own cost in a completely selfish way. I want to minimize my cost. I don't care about the others. If they pay more, this is their problem. This is not mine. So an equilibrium, once again, this is a compromise. And so the notion of compromise is due to Nash, and this is the one that we are going to use. This is basically this notion. I'm going to describe what it means. So when you have a star, so in my lectures, when you have a star, it means that this is either an optimum or an equilibrium. So each time you see a star, this is to say that it refers to something that is optimal or equilibrium quantities in some way. So I'm saying that you have an equilibrium, so actions 1 up to n is an equilibrium for your game with capital N players if there is no incentive for any players to leave the equilibrium. If I leave the equilibrium, I'm going to pay more. This is what it means. So there is no need for me to leave the equilibrium, as otherwise, if I leave, assuming that the others do not leave, they keep playing the same. If I leave, but the others keep playing the same, then I'm going to increase my cost. So this is what I'm going to call a compromise. So this is exactly what you see here. You see here that, okay, I'm going to replace alpha star I by alpha I. I am deviating. I am player I. I'm deviating. Well, I'm paying more. This is exactly what you see in this inequality. You see that the cost when I use I, but the others are using the star strategies, this cost is greater than the one where everybody is using the star strategies. So I am paying more. So there is no interest for me to leave this compromise situation. Okay. In fact, there is a very, very strong subtlety here, a very big subtlety. It looks a very easy definition, but there is a strong subtlety because it's not clear what it means to freeze the others. When I say that, that's fine, I'm deviating, but the others are keep playing the same strategy, you should say, what does it mean? There are several forms of definition for this in the literature on game theory. So I'm not going to make a big course on game theory. This would be outside my own experience, by the way, my own expertise. But I just want to give you a flavor of the difficulties that you may have. The first answer is to say, well, when I freeze the others, I do freeze the realization of the processes, which means somehow for the same realization of the noises, they are going to play the same realization of their actions. This is what people call open loop control. Okay? This is not very subtle, because certainly you could say, well, if I see that there is someone that is deviating, maybe I'm going to deviate myself in some way. In the sense that what people do in many times in game theory is that they assume that the strategies are in Markov feedback form. It means that when you speak about a strategy, you think of a function. So you see that my notation are a bit lazy because I use the same notation for the action, which is a random variable, and for the feedback function that you have here. So this is this alpha I here. So this one, for those of you who are in the room. So this one. But now on the right, I see alpha I as a function of the states of the others. And usually this is the way you should think of an action. So you see an action as a feedback function. If you know the states of the others, then you compute your action depending on the states of the others. So in many models of bad finance or stochastic control or whatever, this is what you do. The optimal, here, this is not optimal, this is equilibrium. The optimal strategy is given in feedback form. So you know in finance, you know your wealth, you are given the strategy, or you know the state of the market. I am given the strategy. So this is in feedback form. And so here, this will be the analog of this. I know the states of all the others in the population. Then I am computing the action through a feedback function. And then when I say that I am freezing the action, in fact, I am not freezing the realization of the alpha I's. I am freezing the feedback function themselves. And so this is what people call a closed loop equilibrium when I implement the definition of Nash. And if you come back to very baby models, you can see that these are not the same equilibrium. In optimal control, usually these are the same. In game theory, these are not the same in many cases. So you could say, well, it's becoming very complicated. Fortunately, when you pass to the limit, you forget this. Asymptotically, you don't see the difference between open loop and closed loop, which is very fortunate for the rest of these lectures. But you will see that at some point, mostly tomorrow, I will speak about closed loop. And so this is precisely to say that you should have in mind this difference between closed loop and open loop. Okay, another remark is that instead of having a Nash, I could say I'm going to minimize now over the whole state of the population. I don't care about the cost of any of the particles in the population, but I do care about the global cost of the society. So now it means that people are no longer selfish. They are cooperating. There is a kind of chief, and the chief wants to minimize the cost to the society. And players are going to work for the chief. And now the notion of equilibrium is no longer the same. I'm going to come to this next. A very simple example. This is an example that comes back from early lectures by Nasri, Lyons, and Guéant. Olivier Guéant, certainly many of you know him. So he was a former PhD student of Pierre Lyons, and they did a very nice survey in the very first lectures of the theory. This is in the Paris-Princeton lecture 208, and they did around 100 of pages about examples. And so this is one example that they had. So you have a collection of producers of energy, okay, electricity or whatever. And so you see that, no, this is not electricity, this is oil, sorry, this is oil producers. And XI should account for the reserve of the producers, or the estimation of the reserve of the producers. And so alpha I is the rate of production. So you see that for sure you decrease the reserve, and there might be some shocks in the estimation of the reserves. And so the larger the size of the reserve, somehow the larger the shocks. So you have a diffusion coefficient that is multiplicative here. Actually, the dynamics do not really care in the rest of the example. This is a very baby example to explain to you the philosophy and to give you, in fact, more insight about more complex models. The main constraint that I have is that the reserve should stay positive. I'm not going to discuss this, but in fact, in what I'm going to say next, we don't really see X appearing, but X appears in the sense that it should remain positive. So there should be a constraint in my model. And now you say, I'm going to maximize. Okay, here I'm sorry, I'm not minimizing, I'm maximizing. So I'm going to maximize the profit. And the profit is given here. This is on this line. Very first difference, this is not in finite time. This is in infinite horizon. This is another class of models that you can have for mean-field games. There are many models in infinite horizon. So you may have ergodic models. This is not the case. Here, what you have is that you have a discount, which is not very surprising for those of you who know finance. So this is a discount, and in the profit, in the instantaneous profit, so this is somehow my running cost, but now this is a running reward. I have the rate of production and the selling price P. The selling price P is a global quantity. This is a kind of aggregate between all the players. And there are some cost of production. I'm not going to describe a function C for the cost of production, and I assume a kind of symmetry between the particles or between the producers, in the sense that all of them use the same cost production. You may have subpopulations with different function C. This would be a kind of generalization. And now, what would be the key points? The key point would be to say, well, the instantaneous price of oil could be given in terms of a function, let's say of the demand. Here there is no demand, but there could be the demand. I'm going to come back to this next. And the instantaneous production in the population. So this would be a baby model. And if I do this, I'm going to see the price as being a function of the aggregate production at the same time t. And so now you see that there is a big interaction between the individuals, and you see that the model is more complicated than the models that I talked about before, because now the mean field interaction is not on the state of the particles, but on the actions. This is what people call mean field games of control. And there is one specialist in the CMAP who is Fabrice Jeté. So you can discuss with him. This was part of his PhD thesis. I'm not going to mention these models. Nizar worked as well on these models, but this is to say that this is a new trend in mean field games. If I wanted to insert the demand, I could assume that the demand is stochastic. The demand could be subjected to some cost, and then this would be a kind of common noise in my population, because this would be a demand that would be the same for all the particles. This would be random, and so this would be a way to randomize the state of the population. So this is another way to think of the common noise. This is a kind of macroscopic quantity that is impacting all the players and that behaves randomly. So once again, mean field games of control. Some people, I forgot to mention Fabrice, who did a nice result very recently. But these are all earlier works in this direction. Okay, just to come back to central planner, just to explain to you what is the difference. Central planner, you come back to the same model as before. The dynamics would be the same. So this is the very top line that you have here. So these are the same dynamics. So this looks a bit strange, same dynamics, and the same cost functional. So you could say, well, what is the difference? So here the cost functional would be the same as before. But this is in the meaning of an equilibrium that I'm going to change my definition. So now I'm saying that somehow there is a central planner who is deciding of the strategy that everybody is now using. So you have the small companies, they are just working on their level, but the policy is prescribed by a chief that is on the top of all the small companies. And what it means is, it means that if you think of the policies or the actions as a feedback function of the states of the others, you could assume that the chief says, okay, everybody is using the same feedback function. This is the policy of the society. Now the small workers of the company, or the small individuals, or the small clans are going to implement the same feedback strategy. So now the particle system becomes a standard particle system in mean field models, except for the fact that alpha is a policy, alpha is a control. And what you want to do is to optimize the global cost, which is in fact the cost to any of the player and the population, because they are completely identical on the statistical level. And so you want to minimize with respect to alpha. So this is not the same. This is absolutely not the same. It does not lead to the same kind of equilibrium when n is finite, nor when is equal to infinity. And I will show you what is the difference. But there are some connections between this problem and mean field models, and mean field games. Okay. So this was the first part about the original motivation. And now I'm going to follow my program and to say, I would like to pass to the limit when n tends to infinity. In fact, I'm not going to do that directly. This would be very, very difficult to do this directly. And you will see tomorrow some tools about to pass to the limit properly when n tends to infinity. So what I'm going to do first is to derive intuitively what should be the model when n is equal to infinity. And first, we are going to study in deep this problem when n is equal to infinity. And once we have well understood the problem n is equal to infinity, we come back to the connection with a finite number of particles. So for those of you who know this, I'm sorry, but I'm going to come back to Makin-Vlasov SDs. And I know that some of you are experts about this. To simplify, no common noise. When there is a common noise, you will see that things are much more subtle because the state of the population is going to be random. So the unknown is more difficult to study. So this is just to refresh your mind, at least for those of you who are not completely aware of Makin-Vlasov equations. And this is one step in the theory. So there is certainly there is an interest for you to have this this part. So there is no control, no control. Okay. So you see, this is a very standard particle system, the same as before, but there is no common noise. So sigma naught is equal to 0. No common noise. There could be. There are some Makin-Vazov models with a common noise, but here there is not. And you see that in the drift, there is no alpha. So no action, no control. And mu bar is as before. This is the empirical state of the population. And I'm wondering about the limit of this particle system as capital N tends to infinity. Okay, so this is the limiting equation will be what we call the Makin-Vazov equation. To pass to the limit, you need a little bit of assumptions on your model. And this is a good reason for me, or a good point for me, to introduce an object on the space of probability measures that is very, very useful. Maybe I presume that many of you know this object. This is the Wasserstein distance. So this is a distance on the space of probability measures. So you will see that at the end of the day, we will work many, many often on the space of probability measures. And so clearly we need some topological properties. And so we need a distance on this. There are plenty of distances on the space of probability measures, but there is one class of distances that is very well adaptive to our needs, which is the class of Wasserstein distances. And here I'm going to use Wasserstein for p is equal to 2, because once again, p is equal to 2 is very nice. There is L2 structure behind, so this is very convenient. So let me remind you the definition if you are not very aware of this definition. So this is to measure the distance between two states of the population, not of individual players. So you take mu and nu, two probability measures, and you want to see what is the distance between these two probability measures. And so what you do is that you take coupling measures pi. So pi is a measure on the product space. So mu and nu are probability measures on RD. Okay, and you have a look at the product RD times RD. On the product space, you can have a look at probability measures which are couplings between mu and nu, in the sense that the first marginal is mu and the second marginal is nu. If you think of random variables, somehow you think of pi as the law of x1, x2, and you require that the law of x1 is mu and the law of x2 is nu. And somehow you care about the joint law of the two random variables. This is exactly what you do. And so now you minimize over pi, which is exactly what people do in optimal transportation, and they are experts of optimal transportation in the room. And so this is exactly what you do. And so you want to minimize the L2 distance between the first and the second coordinates. Why is this very, very adapted for probabilistic or probabilistic arguments? Is that now if you take the Wasserstein distance between the law of x and the law of x prime, two random variables, there is a trivial, so you are given the random variables, and you have to remember that our models are given. So most of the time we already have random variables, and then we have a look at the distribution of those random variables. So you could say that we know what is x. This is modeling the state of my particle at a given time. This is the same for x prime, but maybe for another choice of the strategy. And I want to have a look at the Wasserstein distance between the two distributions, and there is a trivial coupling, which is the joint law of x and x prime. And so I have this inequality that when an x and x prime are given, the Wasserstein distance between the law of x and the law of x prime is less than the L2 distance between the two random variables. And this is very, very, very well adapted to probabilistic arguments. And if you have a look at references in this theory, you will see these arguments many, many times. One exercise for those of you who like exercises, you take an instance, you take empirical measures or uniform measures on finite sets, and you have a look at the distances between two uniform measures on sets of cardinal n in RD. And so you see that I claim that the Wasserstein distance between the two empirical measures is less than the L2 distance in RD with a suitable weight 1 over n in front of the sum. This is exactly the top inequality for a well-chosen probability space. I have to say that all these slides are online on my webpage. Maybe I will give you this at the end of this talk. And when you have a button like this, you can find some very small generalization or extension. So here, this is to say that you can generalize the L2, the W distance to the case when P is equal to 2. And here you have, for the next one, you have a very sketch of the proof to this exercise. So this is what I told you. You choose one possible random variable, and then you have this upper bound. So once again, this is on my webpage, and I will give you the address at the end of this talk. Okay, I have this. I postulate that when n tends to infinity, my particle system is going to solve in the limit what I'm going to call a Makin-Vazov equation. So there is a limit, and the limit, in fact, is described in terms of a kind of nonlinear stochastic differential equation. We say nonlinear because in the equation that you have on the top here, you see that in the drift now, you replace the empirical distribution by the law of the particle itself. So what happens? I'm saying, well, in the particle system, all the players have the same statistical behavior. So they are identical in law. And you see that asymptotically, they are less and less correlated if you come back to the particle system, because in the empirical distribution, I have 1 over n in front of the empirical measure for any delta mass, and the noises are independent. So when n tends to infinity, I see less and less the dependencies on the other noises. So certainly there should be some decorrelation in the population. If I have decorrelation and identical distribution, I should have a law of large number. So clearly I should expect that the empirical distribution of the system gets closer and closer to some deterministic law or theoretical law. And this is exactly what happens. The empirical measure in the system converges to some theoretical distribution. But you see that this is not trivial. This is not trivial in the sense that the empirical measure is random, but in the limit, this is not random. The object that you have here, this L of xt, this is the law of the random variable. This is a deterministic object, which is not random. It describes theoretically the state of the population. Okay, you say I am given this equation. I postulate that this should be the right equation, just because I replace the empirical interaction or the empirical measure by the theoretical distribution. The very first question: is this equation solvable? What people do, I'm not going to make a big lecture about this, but just to give you some arguments about this. Usually people say, I apply the usual Cauchy-Lipschitz theory. I assume that I have a kind of Lipschitz property. Lipschitz with respect to what? Let's say with respect to L2 distance. So in fact, I'm going to assume that B and sigma are Lipschitz usually in RD and Lipschitz in the measure argument with respect to Wasserstein. And the key point, if you assume this, as before, if you take two random variables, xt and x prime, and you take the L2 norm between the coefficients, then this is upper bounded by a constant times the L2 norm, to the square here because I put some square, of between x and x prime. And if you remember any proof by Cauchy-Lipschitz for ODEs or SDEs, this is exactly the type of inequality that you use to implement the usual Cronwall argument and to get existence and uniqueness. It works in the same way. And so you have existence and uniqueness to the limiting equation. Once you have existence and uniqueness to the limiting equation, you wonder whether indeed this limiting equation is the right limiting equation. You have solved the equation, you know that there is a unique solution. Is this unique solution the limit of my particle system? This is what people call propagation of chaos. Why propagation of chaos? Because you started from the particle system with independent initial conditions, independent noises, and you will see that asymptotically, when n tends to infinity, the particles are independent. So you propagated chaos from the initial conditions and the noises to the solution of the particle system when n tends to infinity. When n is finite, there are some correlations. But I told you that decorrelation occurs when n tends to infinity. Okay, so these are very simple results that you can find in the literature. I think that I have some references. If not, I'm going to give you a few names of people who work in this field, and there are some people in the CMAP, so I should certainly quote them. So the very first result is that if you take in your particle system, so my notation is a bit sloppy here, because in fact I should say that on the left here, those particles depend on n. So this is when n is fixed. So when n is fixed, you have a look at k first states, or the states of the k first individuals in the population. And when n tends to infinity, I am claiming that in law, also the law of these people, this converges to the law of the solution to the Mac-Inverse equation, product k times, which means that asymptotically the particles become independent and they behave in the same way from the statistical point of view. And this statistical point of view is exactly the same as the solution of the Mac-Inverse equation. So they get independent in the limit, and asymptotically they solve the Mac-Inverse equation. This is exactly what I told you, and you can prove this. Explicitly. And a side result. Sorry about this black button. It's going to disappear. So the side result is that you have that the empirical measure of the system converges for some suitable topology towards the law of the Mac-Inverse equation. So you have everything that you want. You can have some rate of convergence. We know many things about these equations. The very bad things occur when the equations are driven by singular coefficients. Here they are Lipschitz. This is nice. You have very difficult equations when the coefficients are no longer Lipschitz and they have some singularities. And once again, there are some people in the room that know these questions. Okay, so this is propagation of chaos. I don't remember whether I have. No, I don't have. So a few references for those of you who want to study this. There is one Saint-Flour lecture by Schnittmann, 92. Very nice. And there are some very nice papers by Sylvie Meller as well, who worked more or less at the same time on this question by using slightly different approaches. So Schnittmann and Meller, these are very nice. Tom Course as well did many things in this direction. Okay. This is when there were no controls in my problem. Now let me restore the presence of the control, which is exactly what I want to do. What is the guess? I'm coming back to the mean field gains, to the gain. So now there is really an optimization layer. And what I'm going to say, this is not a proof. This is a way to derive intuitively what should be the asymptotic formulation. This is my very first step. Exactly as I did for the Mac-Inverse equation. First, I said, I am able to derive an asymptotic equation. I'm going to study this asymptotic equation. And next, I study the distance between the asymptotic and the finite version. Now I do the same for the gain. This is more difficult because you have the optimization layer. The guess is that when you come back to the equilibrium, so remember that when you have a star, it means that this is an equilibrium. The guess is that you should see the symmetry in the shape of the feedback function. And typically, this is what happens. So you see that I postulate, you can check that this is, and I'm going to say more about this tomorrow. I postulate that, in fact, everybody is going to use the same feedback function, except that this is reordered in the shape of this feedback at equilibrium. So at the first variable is xi. This is a kind of dominant variable. When I compute my equilibrium feedback, I first implement my own state. Okay, depending on where I am in the state, I will have different actions. First dependence, and the second argument is that I see the orders through the empirical distribution. Okay, so certainly it makes sense to say, when I compute an equilibrium strategy, I will be able to benefit from the symmetric structure of the problem, and certainly, at least in nice examples, my equilibrium strategy is a function of my own state and the state of the population. If you remember the shape of the coefficients, this is exactly the same. So I'm going to preserve certainly the shape of the coefficients. Now, what is very, very more difficult is that this function depends on capital N. Now, this is what you observe in practice. If I had more time, I could solve a practical model by doing all the computations, and you would see that this function alpha n indeed does depend on capital N. So when n moves, alpha n moves. And so now you see the difficulty. You have functions alpha n, which are defined on very, very big spaces because you have many, many, many players. In fact, asymptotically, I'm going to see a measure. So this is infinite dimensional. And so trying to pass to the limit on functions which are defined on very, very big spaces, this is more complicated because it means that if you wanted to do that, you would need some a priori estimates on the regularity of these functions. This is very difficult to do. This is the reason why at this stage, this is just an intuitive argument. Anyway, the guess is that asymptotically, alpha n should stabilize. So they should be approximately equal to some alpha, not depending on n. This is my claim. I say, well, assume that I am able to do that. I am coming back to the particle system, and I say, if I replace at equilibrium, if I replace the equilibrium strategies by this approximation for the same alpha, I recover a Makin-Vazov particle system, a particle system of the same type as in the previous slides. Okay, I have this alpha, but alpha depends on xi and depends on mu bar. So this is a particle system of the same type as before. So certainly it means that the empirical measures are going to stabilize around the theoretical measures. So it means that certainly this mu bar n that you have here are going to converge to some mu t, which is deterministic. There is no common noise in my story at this level. This would be more difficult with a common noise. So this is my claim. To come back to a particle system, you say certainly alpha n is going to stabilize, and then I expect that when n tends to infinity, mu n, which is deterministic, should be very close to something that is deterministic. So in words, I should get the description of the global state of the population in equilibrium by means of this mu t. This is an interesting information, but this is not what I want. What I want is to have an intrinsic description of mu t. Mu t is going to the limit of this particle system. Mu t should be the statistical state of the population at equilibrium. Possibly there could be several equilibria, but mu t should describe statistically the state of one equilibrium in the population when n gets larger and larger. And so the question that I am wondering is, what is an intrinsic formulation or description of this mu t? And this is the next slide, and this is the main slide in this lecture this morning. I'm going to define mu t, so the statistical state of the population when n tends to infinity, as the solution of the fixed point problem. Fixed point is pretty usual in games. Usually equilibria in games are given by fixed point, and here this will be a fixed point on the space of probability measures, depending on time as well. So this is what I'm going to do. I want to find an equilibrium state in the population. So once again, I am describing the state of the population at equilibrium, keeping in mind that time evolves. So this is a collection of probability measures indexed by time. So since it's going to be a fixed point, I am given a candidate for being the fixed point. So you have that this is your flow mu t here. This flow of probability measure is a candidate for being an equilibrium. So any time t, mu t should be the state of the population or the law your particles, if you think, if you want to think in terms of laws, at a given time t. And I say, first point, I want to implement the same idea as in the Nash equilibrium. When the environment given by the others is prescribed, there is no incentive for one player to exit or to leave the equilibrium. So now you see that the environment is described by μt. This is your statistical description of the environment. This is the population where you are living or within you are living, and you take one person in this population. In particle system, we would say this is a tagged particle. And so this tagged particle is solving this equation. This is the same equation as before, but I have replaced the empirical system by μt. I am not saying that μt is the law of xt. I'm not doing this at this moment. No, I'm saying μt describes the state of my population. And within this environment, I have one particle, a tagged particle, that is going to evolve, and I'm going to see what to do with this particle. And with this particle, I can assign a cost, the same cost as before. This is the cost that this particle is going to pay when playing the strategy alpha. So alpha is my action. And in my cost, I see the potential interaction or the potential energy with the rest of the population. And this is described by means of this μt. So I have G of μt and F of μt. Once again, this μt is not the law of X. This is my candidate for being the equilibrium. And this is the way I describe the state of the population. And I say, okay, what does Nash say? Nash says that given μt, I should minimize. I should minimize. I am given the states of the others. What I want to do is to minimize my own cost. So I minimize. To simplify, I assume that there is a unique minimizer, and for sure you have some generalization about this, what happens when the minimizer is not unique. You can guess that there are certainly several mathematical extensions, but this is the very first step. You call X star. Star is, once again, always equilibria or minimizers or optimizers. This is the optimal path under the environment μt. I have described the others. I am minimizing. And now, once again, I recall Nash. What does Nash say? It says, at the equilibrium, there is no incentive for me to exit. So here, if μt is an equilibrium, it means that the law of the optimizer should be the environment itself. So it means that the law of X star, the law after the best response, is the environment. This is the Nash condition. The best response when the others are frozen is in fact described is describing the Nash, the equilibrium itself. So the fixed point is exactly given at this level. So I am minimizing, computing the best response, and I say, well, Nash says that the best response is exactly the environment. And so what I have to solve for solving a min-field game is to solve this fixed point. Now the question is how to do that. And you see that you have PDE ways or probabilistic ways. Certainly there are many connections between the two of them. If you do PDE, and this is what I'm going to do first because certainly this is easier to explain, and then I will say a few about probability, but there are many, many connections. If you do PDE, you have to reformulate all this problem in terms of PDEs. And then you end up with a fixed point on the system of PDEs, or you get a system of PDEs, which is exactly the original system of PDEs that Lasry and Nyons introduced 15 years ago. I claim, last line, bottom line on the slide, what I said is not a proof of convergence. This was just a purely intuitive way to derive the formulation of the problem. Now the analysis of the convergence, as you will see, remains much, much more difficult. So now this is the formulation. So we have seen, so just before the break, so how to formulate asymptotically the game. And so this was the definition of a min-field game in terms of a fixed point. And so now we reformulate this fixed point in terms of PDEs. And so you will see that we obtain a system of 2 PDEs. And this is the starting point of a big literature that you have in the field. So if you don't know that much stochastic control, let me make the following reminder. When you have a stochastic control problem, there are two strategies. The first one is the probabilistic point of view, which would be a kind of Lagrangian point of view. You sit down on the particle and you see what happens. Another point of view is a more Eulerian point of view. You are sitting at a given time and a given point, and then you want to compute how much you have to pay till the end. And so this point of view gives an equation, a PDE, that is called Hamilton-Jacobi-Bellman equation. So this is what we call an equation for the value function. So this value function, this is the little u that you have in this definition. So it depends on mu. So mu is the same as before. This is describing the state of your population. This is the candidate for being an equilibrium. And so you are prescribing the interaction here with the population, mu t and mu s. And you see that you regard the best possible cost till the end when you start your initial state from little x at time t. So the environment is given, and you solve the usual stochastic control problem. And this is the value function. So once again, this is the best cost you have to pay till the end. So hence the reason why you start this interval from little t, because this is the running cost from now till the end. And this is one key result of stochastic control, to say that U solves the PDE, which is a Hamilton-Jacobi equation. So this is the shape of the equation. So here I simplified a little bit the analysis. I said that sigma is the identity, so the volatility is 1, or is the identity if you prefer. This is to simplify. For sure, I could generalize, but the spirit would be absolutely the same. The equations would be certainly much more difficult to solve, but there would be no change in the general philosophy of the problem. And so the shape of this HJB equation is as follows. So this is a PDE. So when you compute, when you write down the PDE, you have a term derivative. You have a Laplace term, and everybody knows here that this Laplace comes from the Brownian motion that you have in the dynamics. And then you have an Hamiltonian that comes from the minimization problem. So at any time t, you are given the state of the population mu t, and so you play alpha. And when you play alpha, you see that you go in the direction b alpha. And here you see that this is a small increment of your value along this direction b. So this is the action of b along the derivative of u. And something also that you have to pay in small time is alpha. So what you do in very small time, in fact, is that you want to choose the best possible alpha to minimize the combination of the running cost and the action of the drift onto the derivative of the value function. And this is what people call the Hamiltonian. And a very, very nice example that I'm going to describe, because certainly this is the one that you have to keep in mind, is given, I think, in this bullet point. Let me check. Yes, so many often I'm going to restrict myself to this very simple setting, but this is simple, but this is very useful to have this example in mind. So you choose B of alpha as being alpha, so you directly control the velocity of the particle, and what you pay, so in your running cost, you split the running cost in the sum of two things. So there is one kinetic energy, the square of your velocity, and one potential energy for the interaction between x and the rest of the population. So this is f of x and u. And when you do that and you compute the Hamiltonian, we say that the structure of f is separated. And so you have, when you minimize, you just have to minimize, to compute the Hamiltonian, you have to minimize b, so which is alpha, times z, which is somehow the derivative of the value function, plus 1/2 alpha squared. And so the optimizer is trivial, And the only thing that you want to compute the Hamiltonian is that you observe that when the gradient of u is equal to z, the minimizer is minus z. And so this is the shape of the Hamilton-Jacobi equation. So this is the baby example we can guess for the Hamilton-Jacobi equation. And certainly this is a way to visualize what it means. You get a PDE for the value function that is nonlinear. And you see the impact of the nonlinearity in this model. Here, this is the square of the gradient. So this is one classical equation in stochastic control. The very spice of this equation is that for sure the cost here, F, depends on ut, depends on the state of the population. So you can keep in mind this equation as a kind of toy model, but in fact, very interesting, but toy model for your HJB equation. But keep in mind that the cost, the source term that you have inside depends on the state of the population. And so you have to give a boundary condition for this equation. And this is given by the terminal cost. This is how much you have to pay in the end. And so this is U of capital T that is given by G computed at mu capital T. So this is what I'm going to say back to my original slide. So once again, I will give you the address, and maybe this will be posted on the website of the course, so to have access to the slides, and so you will find all these computations on the website. So back to this. So I told you, well, when you are given the Hamiltonian, so you compute alpha star depending on the private state, on the state of the population, on the value of the gradient of the value function. And what you do, in fact, is you say, my feedback function, my optimal strategy, is a function of my state, the state of the population, and the derivative of the value function. Okay, so this is the optimal strategy that you have to play, and you see that this is in feedback form when you are given the candidate mu t. Now you have to close the loop and to say that in a mean-field game, you want the law of the optimizer to be equal to the candidate for solving the equilibrium itself. So you have to say that once you have chosen this optimizer, once you have chosen this feedback function, and you implement some dynamics driven by this feedback function, the law of it is exactly mu t itself. So keep in mind, here we have a Hamilton-Jacobi equation that is backward. This is part of the feature of the model because the terminal cost here, it prescribes the boundary condition at the end of time for my equation. And so next slide is to say, I want to implement the Nash property, the fixed point property. I am saying that at equilibrium, I am playing the feedback function that was given before. So in my baby model, in my toy model, this would be just minus the gradient of u. It seems very simple, but even that, in the end, you have some complications. When I have a process, a diffusion process, which is exactly the case here, I know how to compute the evolution of the marginal laws. This is what people call a Fokker-Planck equation. So I had a Hamilton-Jacobi equation for the value function, first equation, and second equation, this is a Fokker-Planck equation. This is what I call here. And to compute this Fokker-Planck equation, certainly you have this button you can press if you want. So this is just to make the exercise for you if you don't see exactly how to do that. So when you have an Ito process or a diffusion process solving this equation, and you want to compute the law of X, I'm claiming that the law, the marginal law, solves a Fokker-Planck equation. So you see that you have the Laplace for the noise, and here you have the divergence of B times mu. And the way you do that, you just test the test function phi. You take a test function phi, acting on the solution of the equation. You expand by Ito's formula. You take expectation, and then you get a weak formulation for mu t. This is the way you get the equation, the Fokker-Planck equation. So for those of you who want to see that, you can go back to the slides once this is online, And okay, there is no button back, is there? Yeah, there is. Okay, so this is the equation I have for mu t, and so this is exactly minus the divergence of B and B of alpha star dx mu. Okay, so I implement the optimal feedback depending on u through the value of the AJB equation. You can write down explicitly the two equations again. Let me mention the difficulty of these two equations. There is one Fokker-Planck equation that runs in the forward sense, because what you know is the initial state of the population. This is the boundary condition of it. And there is a backward Hamilton-Jacobi equation that runs backwards, because the boundary condition is given at the terminal time. And so you have two directions of time which are conflicting, and this is the very difficulty of the analysis. If you don't believe me, what would be the finite dimensional analog of my problem? There is a mistake on the slide. There is no dt in these equations. I'm sorry about this. So you take a forward equation that would be an ordinary differential equation, even in dimension 1. The velocity x dot would be given by b of x, and b would depend on yt. And yt would solve another ordinary differential equation, but with a terminal boundary condition, depending on the value of x. So this is what we call a two-point boundary problem. And if you try to implement any Cauchy-Lipschitz theory, it fails, because you have two conflicting directions of time, except if time is very, very small. But if time is arbitrary, then it fails. And you have plenty of counterexamples, even in finite dimension, where you lose either uniqueness or existence. So certainly, if you have some difficulties in the finite dimension, certainly this will be quite messy in infinite dimension. And this is the reason why the system is far from being easy to solve. So think of the difficulty here, beside the equations themselves. Think of the fact that we have a forward-backward system. You have this terminology that comes often and often in the mean-field game theory. You have two conflicting directions of time. So this is one way to formulate the analysis, one AJB equation and one Fokker-Planck equation. Now I'm going to show you that, in fact, you can reformulate this by probabilistic arguments. I'm not claiming that you get results that are completely different from the PDE point of view, but it becomes useful to have this in mind when you try to generalize the model. This is useful to have several approaches, because when the model becomes very complex, either you can choose between one of the two approaches, or you can take elements from one approach and then combine with elements from another approach. And so this is always useful in maths to have several approaches for the same question. So this is what people call forward-backward SDEs formulation. I'm not going to say that much, but I just want to say a little bit of it, because this is quite useful in the field. So it comes back to another formulation of the optimal points of a stochastic control problem. So once again, I am coming back to mu t frozen, and I'm writing down some equations to say what it means to be optimal, and then I end up with a fixed point to say that this should be the solution to the mean-field game. So generally speaking, I'm going to explain this to you next. You can describe the optimal trajectories in terms, so when mu is frozen, in terms of a coupled forward-backward system. So this is not coupled forward-backward as before between two PDEs, but this is between two SDEs. So the solution here, the notation here is not very rigorous. This is to say that the forward equation, you are going to replace alpha either by y or z. I'm sorry about my notation. This is not a very good notation. And y or z, this is given by the solution of a backward stochastic differential equation. So if you don't like it, you can forget it. But if you like it, please listen to what I'm going to say next. So y is, this is a value somehow in in this equation, but the very spice of a backward stochastic differential equation is that the unknown is not only the value y, but this is also this integrand z that appears in a kind of compensator term. This is the kind of penalization that you have here in the equation. In fact, if you remove the last term, the equation that you get, this is a kind of ordinary differential equation that is set in the backward sense. You would have that yt at the end is given by capital G of xt. I'm not saying now what is capital G. This is not the same as little g before. I'm going to say that next. And then the derivative in time would be minus capital F. And once again, I'm going to tell you next what is this capital F. But the very bad point of this, if you do that, if you solve the ordinary differential equation, is that the solution yt is going to anticipate on the future of the noise. So because you want to reach a terminal value, the terminal value is going to depend on the whole path, on the whole noise w from 0 to capital T. And if you solve your ordinary differential equation without the penalization, you will get that the initial value y0 is anticipative on the future of the noise. And everybody knows that usually this is exactly what you don't want to do in stochastic analysis. I know that some people do anticipative calculus, but usually you try to avoid this. So there is a way which is to penalize. You penalize the equation in a unique manner to force the solution to be adapted to the noise. This is the theory of backward stochastic differential equations that comes from Pardue and Peng in the 90s. And there are some experts in the room. Now, once you have this term z, once again, this is an integrand in this penalization, and somehow it's determined in a unique manner. And back to the forward equation, you can either use y or z as an information to represent the optimal trajectory. It completely depends on what you put as f and g in the backward equation. And basically, there are two ways. The first one is either you represent the value of the game and you follow the value of the game along the optimal trajectory. This will be y. And then you use z in the backward equation, z in the drift, or you represent the evolution of the derivative of the value, which is more or less the action. You follow the optimal action, which is exactly what you do in the Pontryagin principle. And then you will use y instead of z in B. So this is what I'm going to say next. Now, so if you choose G is equal to F here, if you choose G is equal to F, basically you are going to represent the value function. Well, I'm a bit lazy here because I did not really mention where would be the optimal cost. So the optimal cost in that case, this would be Z. Basically, when you do, you represent the value of the game, the value of the minimization problem. The optimal trajectory is somewhat regarded as being Z, so the representation of the martingale. Now there is another strategy, which is to choose capital G and capital F as the derivative of the cost G and the derivative of the Hamiltonian. And then this is exactly what people do with the Pontryagin principle. So there are the two ways. This is things in stochastic control theory. Either you sit on the particle and you follow the remaining cost that you have to pay till the end, or you sit on the particle and you represent the optimal strategy that you have to pay, which is exactly what you do in the Pontryagin principle. And then whether you work with the first one or the second one, you choose either GF as being little g, little f, or capital G, capital F being the derivative of the little g and the Hamiltonian. So you have the two of them in the literature. But the spice of it, and certainly this is the only thing that you have to remember at this stage of the lectures, is that once you have solved this forward-backward system, to get or to solve the mean field game, what you want to do is just to say that you replace mu t by the law of x. So in the end, you say, well, in fact, to have the solution of a mean field game, I should have that mu is the law of x. And then you get what people call forward-backward system of the Mackintosh of time. So this is what you have in the literature. You can find this is in my book with Carbonell, for instance. maybe I can try to clarify just for those of you who really want to know. So if you want to represent the value of the game, so this is basically what you have. So the optimal trajectory, you see that this depends on the law of X, and then you implement alpha star at Z. So once again, Z, which is given by the backward equation and the integrand in the backward equation, really it tells you how you have to, which strategy you have to play. And then this Y is going to describe, once again, the evolution of the cost when you sit down on the particles. So this is one type of forward-backward system that you can have of the Mac-Inverse type. And another one, so once again, yes, if you really want to see the connection with the PD formulation, Y is the cost that you have to pay when you sit down on the particle. So capital X is the optimal trajectory. You sit on the optimal trajectory and you compute how much do you have to pay. And Z in this is dxu, so this is very much related to the optimal trajectory, to the optimal control, or to the feedback function. Now, another strategy, as I said before, is to use Pontryagin principle directly to represent the evolution of the optimal feedback function. Well, these are some conditions under which you can apply these arguments. I don't want to describe too much. If you want, you can see a bit on the slides, and I can discuss this with you personally, but I don't think that this is really needed to describe some conditions for which this works. So another approach, as I said, you represent yt as being connected with the derivative of the value function. So this is what you have here. So you see that this is not the same. You represent the derivative of the value function. So somehow you sit on the particle and you see what is the optimal strategy. You follow the optimal strategy. So these are not exactly the same points of view. And so this is what we call the Pontryagin principle in stochastic control. And once again, you have this penalization here by the stochastic integral to force the non-anticipativity of the solution to the equation. And once again, you have that this is Macklin-Vlasov in the sense that the law of the solution is exactly, or drives the interaction, the mean field interaction, or is in the end the equilibrium for the population. So keep in mind, we have three formulations, the PD1, which is certainly the one I'm going to use next most of the time, and two forward-backward formulations, and sometimes in finance, or in other words, maybe for energy markets as well, people use this formulation, but certainly this is connected to the PD1. Either you sit down on the particle and you follow the cost, or you sit down on the particle and you follow the optimal trajectory, the optimal strategy. And these are conditions, but I don't want to enter these details. Okay. How much time do I have? Not that much. I would like to say a few words about how to solve a mean field game. So we started from the particle system. Then we got formulation of a mean field game, and I told you fixed point problem, PDE formulation in terms of a forward-backward system, and then two possible forward-backward equations of the stochastic type. Now, how to solve this this problem. This is a fixed point, so you could say I'm going to use a contraction argument. But if you remember what I told you about the analysis of two ordinary differential equations with two different time directions, certainly this is a bit hopeless. And indeed, if you do that, there is basically no way to get a contraction under general assumptions, except if time is small. If time is small, you can get a contraction. And in fact, if you go to the very first papers in the field, not the paper by Lasrenius, but mostly the paper in engineering, you will find many, many times some conditions on the coefficients. You will see that there are some intricate conditions that require time in the Lipschitz coefficients of the Lipschitz constant of the coefficients to be small enough. And this is exactly to get a contraction. But this is very limiting from a practical point of view, because most of the time this is not what you have. So you have to forget contraction arguments. So then you can jump to possibly other types of fixed point results, but without uniqueness. And typically you have a class of fixed point theorems without uniqueness. This is in infinite dimension. These are Schauder theorem. I'm going to remember to recall you what is a Schauder theorem. But once again, if you go to many papers in infinite games, you will find either Schauder or Kakutani theorem. These are classes of theorems for which you get a fixed point without using contraction. So just by some topological arguments, you can get existence of a fixed point, but you don't know uniqueness. And in fact, as I'm going to say next, uniqueness is very rare. Non-uniqueness is the typical regime in mean field games, which is a very subtle issue. This is a very subtle issue from the numerical point of view because it means that many times you are missing a stability. So think of numerical methods without stability. Don't have stability because basically you don't have uniqueness. And even from a theoretical point of view, and I will say more about this tomorrow, if you don't have uniqueness and you have several equilibria, is there one equilibrium that you should choose and that would be better than the other ones? This is absolutely a natural question that you should keep in mind. So these are questions that I'm going to address tomorrow. So once again, you have this Schauder theorem that is certainly one way to get existence. So this is for models without common nodes. When there is a common node, this is much more subtle. I will say a word about this in the afternoon. So a short reminder, I'm sorry for those of you who know this already, this is basically the shape of the Schauder theorem. So you assume that you have a norm vector space. So V is your norm vector space. Double bar is your norm, and then you have a subset that is not empty, that is included in V, and you assume that this is closed and convex. Okay, first point. And the second point is that you have a continuous mapping for the double bar that maps E into E, and such that the image of E by phi is relatively compact. Then you get a fixed point. Okay, so this is a result from functional analysis that is in fact very well known in PDE theory. They're useful for nonlinear equations. And so the question is how to use this result for mean field games. I don't want to spend too much time on this, but just to give you one flavor about it and to show you why it works basically in mean field games, in standard mean field games. For sure, you can guess of more difficult situations. So here we want, so the question is what is V, what is E? And typically what we want is to have E to be included in a collection of continuous paths. So C, the symbol C that you have on the slide here, this is for continuous. So you have a look at continuous path of time, 0t is for time, with values in the space of probability measures. So these are the evolution of your population. So certainly E must be included in this because you are seeking for a solution within this space. Now, if you want to have a vector space, you have to embed your probability measures with a space of measures or sign measures to have a vector space. And typically what we use is measures for which you have that the integral of x with respect to the absolute value of the measure is finite. Okay, whatever, you can forget the last part, the fact that you embed in M1. This was just to show you that we can embed in a vector space if you really want to apply a Schauder theorem. But anyway, you want to use this space and you are looking for a subset of this space. This is one point. Okay. When you have the space of probability measures, as I told you before, you have plenty of metrics. Okay. There is one topology or one sense of convergence that you know very well. This is the weak convergence. So weak convergence is just to say that nu n is going to converge in the weak sense, or this is Vn here, I'm sorry, Vn converges in the weak sense to V if for any bounded continuous test function, the integral of h dvn converges to h dv. In fact, very first remark, this is pretty easy to have compactness. And remember that compactness is needed in Schroeder theorem. We want the image of phi of E by phi to be compact. This is very easy to have compactness for probability measures. We know this. These are tightness results. Basically, we don't want the mass of the measures to go to the infinity. We want to control uniformly the way the mass goes to infinity. This is the way I should say that. Or conversely, if I have probability measures on a compact set, then they are automatically compact. So we have nice criteria. These are Prokhorov theorem for probability for compactness on the space of probability measures. Now, what is the connection between weak convergence and convergence for the Wasserstein topology? In fact, this is very close. When you have weak convergence, this is almost convergence for W2. The only thing to get W2 is that you need uniform square integrability. So this is a stronger way to control the decay at infinity of the tails of your probability measure. So remember these two facts. For weak convergence, this is pretty easy to have compactness, tightness, so everybody knows it in probability. And second result, in fact, when you have weak convergence, if you have uniform square integrability, so you control the tails in a sufficiently nice way, in fact, you get convergence for W2. And so at the end of the day, this is pretty easy to have compactness on the space of probability measures equipped with the Wasserstein distance. We know how to do that. For those of you who know optimal transport, you know the book by Villani, and you have a very, very nice chapter about these questions in one of the two books maybe in the two books, but at least in the second one, the second books of a book of Villani on these questions. Okay, so here I'm claiming that we can choose a norm, in fact, on the space of measures, on the space of sign measures that is consistent with the P1 topology, so the one Wasserstein distance, which is this is the Monge-Kantorowicz norm, in fact. So this is a way to say that I can put a nice topology on the vector space that is completely consistent with the topology that I'm going to have in P1. And once I have convergence in P1, this is not that far from P2. Once again, this is a question of controlling the tails of my probability measures. So this is one remark. Another remark is that I need some continuity in Schroeder theorem. I told you when I take an input, I want to map continuously on the output. Here, it comes from the fact that my coefficients, B, F, G, so the drift, the cost, and so on, are going to be continuous with respect to the state of the population. So you need continuity, and most of the time when you have a look at existent results for mean field games, most of the time you have continuity, and continuity is very useful in the application of this kind of Schroeder argument. Okay, I'm not going to make the whole proof. This is just to give you some intuition about the way it works. So certainly here, this is a summary. You have compactness. If you have moments of order p greater than 2, you have uniform square integrability. And so there is convergence in the weak sense and in the W1 and W2 Wasserstein distance, and also for the norm double bar. So I have a nice framework just to say that you can recompile your knowledge in probability theory to apply to this problem. Now, how does it work? So you take this is the description of E. You can forget it. This is just to give you the intuition. If you come back to the dynamics that you had in my mean field game, maybe this is a good point for me to remember the dynamics. Just one before we go into the detail a little bit more. Okay. So I told you to get Wasserstein convergence, whether this is W1, W2, I need weak convergence plus control of the moments. This is very fine. If I have a stochastic differential equation, I know very well how to control the moments of the solution if I have nice assumption on B and sigma. So I will put all I need on B and sigma to be sure that the moments of the solution are controlled uniformly, independently of the input mu. This is what it means. I have this. I will get control on the tails of my random variables or my probability measures. So come back to the proof. This is what you have here. So I'm going to restrict myself to probability measures such that I control uniformly the fourth moment. Okay, this is one way. Once again, you can forget for the square 4. The message is that I want to control the tails uniformly with respect to the input mu. So I am focusing on those path mu t. This is the message out here. Okay, now you say for such a kind for such a mu, I am recalling the shape of the forward-backward system. So I do solve the HJB equation, and once I have solved the HJB equation, I put this into the forward equation, and I know that the forward equation that you have here with alpha star minimizing the Hamiltonian, as I told you before, this is the optimal trajectory. And so what I want to do is that I'm going to say the image, so this is the red box that you have here, this is my mapping phi, and I want a fixed point for this phi. I take an input, and I compute an output by saying I solve HJB, then I solve the SDE, and then the law of the SDE is going to be output. And I want this phi to be continuous with respect to my topology double bar, and I want it to be continuous. I want it to be the image is relatively compact. About the convexity here, remember that I had some closeness convexity assumption here. This is absolutely trivial with this choice. So the only thing here, in fact, this is to say that the mapping is continuous and that the range is relatively compact. And so continuity, I'm going to be quite quick. This is mostly a question of continuity or stability for Hamilton-Jacobi. So if you put nice Hamiltonians, as I did with the square, with the kinetic energy and the potential energy, basically it works. And so you know, specifically because you have the Laplacian, when you have the Laplacian, Hamilton-Jacobi becomes quite easy. And you can have nice controls on the solution independently of the input if you put if you have nice assumptions on the data. So it says that here you can control uniformly here the growth of dxu, so of the derivative of the value function, and then you can control uniformly the growth of the optimal feedback function, and so you can control uniformly the moments of R. And so you close the loop because you say, I have an input with a fourth moments that are going to be bounded by K. And by tuning K well, depending on the stability properties of HJB, I'm going to say that, in fact, I also have that the outputs are in the same subset. And this is the way I have some stability of my set E. Continuity, this will be stability of HJB plus stability to the solution to this Makin-Vazov equation. And compactness, this is tightness, and we know how to get tightness for probability for stochastic processes. And then once you have tightness for stochastic processes, you have tightness for the laws themselves, in fact. So this is for in the weak sense. And once you have weak sense, you combine with the a priori bound on the fourth moment, and you get a compactness for in the set C0T with values in P2. I'm not going to say more. I think that this is what you have to remember, to say that this is not that difficult to get some existence result, provided that you have nice bounds on the coefficients, and then by using the Laplacian, really the Laplacian is very, very useful. When you remove the Laplacian, I'm not an expert of this, then you face a Hamilton-Jacobi of the first order regime, and then this is more subtle. You may have some similarities, and this is much more subtle to study. I'm not going to speak more about this. There are some papers, and there are some experts in this, but as a good probabilist, I'm more used to models with a noise, so hence the presence of the Laplacian. Okay, so this is the conclusion. This is stable. I'm not going to spend much more time, but this is exactly what I told you. Stability using the growth of dxu. And then continuity, this is mostly, as I told you, non-degeneracy of HJB. And then for compactness, I have moments plus weak convergence. Okay, so if you think of the models that I told you before, this was this model, the one that we discussed. I like this model very much. This was this one. So basically, for this model, so the one where we had this very simple HJB equation, if you take a cost F here, let's say to simplify, that is bounded and the same for G and continuous in mu, then this is fine. This is, or maybe continuous in X and mu, depending exactly on what you want for HJB, but you really need continuity in mu, and then this is fine. You get an existence, or you get the existence of an equilibrium. So this is for existence. Now, I think that I have a bit of time. Yes, I have 15 minutes. I would like to say more about uniqueness. So this was for existence, and now let me come back to uniqueness. So this will be my the very last part of my talk today. This morning. So uniqueness. So uniqueness is very more difficult, much more difficult, and this is a quite fascinating question. Just to give you a very simple model, finite dimensional analog of the equation that we are facing. I told you that this was a forward-backward system. So one forward equation, one backward equation. So let me give you the following analog in dimension 1. X dot is minus y. So this is the velocity is minus y, and y dot is equal to 0. Y dot is equal to 0. This is another backward equation, but the spice of it is that the boundary condition for y is at the end of time, and it depends on the state of small x. So this is a two-point boundary product. I claim that this is the characteristics of the Burgers equation. And this is something that we are going to revisit in the afternoon. For the simple reason that if you want, assume that you want to propagate here the fact that yt is g of xt. This is a kind of Markov property somehow. So the Markov property would say that you expect yt to remain of the shape vt of xt. There is no noise here, but you will see that when there is a noise, this is the same somehow. So hence the reason why I say that this is Markov, but there is no noise. So you do that, and you say yt, I expect it to be of the shape yt is vt of xt, and I expand y, I take the derivative in time, and I see what it means for v. And then you find that v has to be the Burgers equation. When you compute the derivative, you compute v dot, you find that in fact, by using the first equation on the top line and the second one here, you see that necessarily v has to solve this equation. And you know that for Burgers, you may have plenty of troubles. You may have some singularities appearing, and this really depends on the shape of the coefficients. And there is one regime that is very nice. This is when f and g are monotone or non-decreasing. When this is non-decreasing, then you may have uniqueness, or you have uniqueness of characteristics. But if you lose monotonicity, or the fact that this is increasing, then you may have some shocks, which means that you lose uniqueness of characteristics, and in terms of the solution, you may have singularities. So let me give you the following instance. I take, so here in this equation, so this is Burgers with f is equal to 0 here. So this is just g that is non-decreasing. So you see that this is the profile of g. So this is constant, it grows linearly, and this is constant again. You plot the solution to the equation. These are the characteristics for different initial values at the initial time, and the interval, the time length is capital 1, or 1, sorry, capital T is equal to 1. And so you see the shape of the characteristics depending on the initial point, sorry. So on the vertical axis, you have the initial state of the equation, or the ODE, or the forward-backward ODE, if you prefer. And so there is no shocks; they are uniquely defined. Now you reverse the shape of the initial profile. So this is what I'm doing in the left. And now you see that when t is equal to 1/2 small time, this is fine. I have uniqueness of characteristics. But if I increase t, here I have a blow up, a singularity. At initial time 0, I have many characteristics. So this is typical. I have plenty of characteristics. I'm losing uniqueness. And in fact, at the level of the PDE, it says that there will be a singularity at the 0. I will have that the front coming from the left is going to meet the front coming from the right. Okay, so since I have a forward-backward system in in infinite dimension, I should face the similar issues. So there is no reason why I could not face this kind, or I could escape this kind of difficulties. So this is to say that if I want to enforce uniqueness, I need a kind of monotonicity in the system. And this is what we call the Lasrillion's monotonicity condition. This is one of the most famous conditions for uniqueness. This is the notion of uniqueness for mean-field games. So you take the same coefficients as before. So G is the running cost, and G is the terminal cost. And in the running cost F, you split the cost into two parts. One that only depends on X and mu, and one that only depends on X and alpha. Think of 1/2 of alpha square, so the kinetic energy. This was an example for this F0. And so you say that this is monotonous if you have this property. So you see, you take mu and mu prime, two probability measures, you compute the cost at the same X, and you integrate the difference between mu minus mu prime, and you require to be non-negative. And you do the same for G. And if you do that, I'm claiming that you get uniqueness. And I think that I have enough time in 8 minutes to show you why you have uniqueness. So this is the main assumption that you will find in literature about uniqueness. This is not the only one, because in fact, the subtle question is that this is related with the notion of convexity on the space of probability measures, but you have different notions of convexity on the space of probability measures. And since you have different notions of convexity, you have different notions of monotonicity. And so there is another notion of monotonicity, which is called the displacement monotonicity, for which you may also have uniqueness. An instance of a function that satisfies this property before I make the proof. So this is an instance of a cost that satisfies this monotonicity property. So H could be either F or G. So you take a loss capital L, and you see that the loss is going to depend on two things. The first one is that it depends on Z, but Z is going to be integrated in the neighborhood of little x. So rho is a small convolution kernel. So think of the support of rho as being very small. So you have x minus z that has to be very small. So when you integrate the loss capital L, z is going to be very, very close to x. So you compute the cost in the neighborhood of x. And in the second argument, you have the convolution rho star mu at point z. Rho star mu is a way to compute the local mass in mu around z and so around x. And so what you say is that hx mu, this is a kind of local loss or loss depending on the local mass in the neighborhood of little x. And I claim that this is monotonous if the loss increases when the second argument increases. And this forces uniqueness. This is a way to say that in models, people don't want to be close together. So if there is some mass at a given point of the space, I don't want to increase the mass, because if I'm going to increase the mass, certainly I'm going to pay more. Okay. So I'm going to prove you that basically you get uniqueness under this monotonicity condition. And to do that, I'm going to assume that when mu is fixed, so the input, the candidate for being an equilibrium is fixed, I'm going to assume that there is one unique optimizer. So for any, not minimizer, not equilibrium, minimizer. So it means that for any state of the environment, there is a unique optimal control, which is exactly the notation that you have here, alpha star mu. So you take two possible equilibria, mu and mu prime. Mu in red, mu prime in blue, and I will try to keep these colors till the end of this proof. And so I have two equilibria, or two equilibria strategies. Alpha star mu, this is the best response under the environment mu, and alpha star mu prime, this is the best response in the environment mu prime. Now you compute the cost. So J mu, this is the cost in the environment mu. well, if you have understood what I've been saying for 2 hours and a half, the best response under mu, this is alpha star mu, so this is less than the best response, the cost under mu when I use alpha star mu prime. Alpha star mu prime, this is the best response in the environment mu prime. And I assume that the two equilibria are not the same. So since they are not the same, the feedback, the controls cannot be the same, as otherwise the two equilibria would be the same. And since I assume that there is a unique minimizer under J mu and J mu prime, the best response here is alpha mu, and so the cost is less than alpha mu prime. And I do the same conversely. Under mu prime, I say that the cost here is less than the cost blue when I compute the red strategy. Okay, I symmetrize. Well, this is a bit of algebra. So you make the difference on the first inequation, the difference on the second inequation, and you make the sum. So you see mu prime mu, this is the right one here. This is this one, mu prime mu, minus mu prime, plus mu prime, minus mu. And the sum is positive strict. You rearrange a little bit. So you see that mu prime mu, I put minus mu, which is the last one, and mu prime with a minus, this is this one, and you say minus mu prime. So this is just a bit of rearrangement. And you write down explicitly what it means. So you compute what it means. And you say, for the first one, I'm just explaining for the running cost, for the terminal cost. This is exactly the same for the running cost because they are separated. The cost F is F0 plus F1, which means that F0 only depends on X and mu. And in F1, I don't see the population. I don't see the state of the population. Maybe I didn't say very clearly that in this assumption, B, the drift, does not depend on mu. B does not depend on mu. So it means that, in fact, when I have mu prime and mu, and when I play the same strategy, I have the same path because the drift doesn't depend on the state of the population. This was on the slide, but I forgot to say that. So when you write down explicitly what it means, this difference for the terminal cost, this is an integral. So you see that this is the same path because this is the same control. And so when you write the difference here, you have g of little x acting on the law. This is the MFG condition. Mu t is the law of this random variable. And here I have mu prime and mu, which are the arguments of g. And you have the same for the other one. So these are for the terminal cost. And now you rearrange a little bit. And you say, well, this is exactly g mu prime minus g mu integrated in mu. And the same g mu prime minus mu integrated in mu prime. And you have to make the difference. And what does monotonicity say is that this difference has to be negative, at least non-positive. And so you have a contradiction, and this is the proof that you have in the class. Okay, so this was, I think, the last slide. Okay, so I'm just on time for this first lecture.